Okay, everybody's going quiet, so it must mean it's time to start. I should announce, just thinking about next term's colloquia, so the first colloquium of the new year, which will be on the first Thursday of the term, I forget what the date is, but so Gordon Walker is going to come and talk to us about the history of exoplanet discovery. So for people that don't know who Gordon Walker is, the UBC story is he discovered exoplanets, and he did get some of the credit. There was a recent Nobel Prize. We thought that rather than getting some of those Nobel Prize winners in, we would get our own Gordon Walker to come and describe us, his version of the story. So that's going to be the start of the year, and then there's a whole semester worth of colloquia arranged. But tonight, I'm very happy to introduce Sean Carroll. Thanks to everybody for coming out on this rainy night in the middle of the exam period. I kind of assume if you're here, you know who Sean Carroll is, so I'm not going to give him a long introduction, but we're very happy that he's come in this, again, off his normal schedule and so on, come specially to talk to us tonight. So Sean.
Great. Thank you very much, Douglas. It's great to be back. It's been a while since I've been here. It's raining out. I don't know if you noticed this. I'm not used to this anymore since I moved to Los Angeles, but that's okay. I survived. I want to talk about quantum mechanics. Some of you may know I recently wrote a book about quantum mechanics, Something Deeply Hidden. If you didn't know that, you could buy it right now on your iPhone without leaving. I would not be in any way upset about that. And why in the world does the world need another book about quantum mechanics? I went to Amazon, I typed the word quantum into the search bar for research for my book, and I found, there's quantum yoga, quantum therapy, quantum healing. None of these have the Schrodinger equation in them, I noticed. And I think that the reason is that we haven't taken quantum mechanics seriously, which is a bizarre thing to say because, of course, quantum mechanics is at the heart of all modern physics. We use quantum mechanics every day, but we use it in the same way that I use my laptop. Right? I can make it do things like project onto the screen, but if you ask me what was going on inside, I have no idea, really, roughly speaking. And that's how physicists used quantum mechanics, and I don't think that's okay. I think we need to learn to do better. And I think it's not just a matter of pride or principle, but we're stuck in certain ways in fundamental physics, issues like quantum gravity, for example, and maybe thinking a little bit more deeply about quantum mechanics is a useful way to go. So I want to start slowly. It's a colloquium. I know it's a heterogeneous audience, so I'll start slowly, but don't worry. By the end of the talk, you will not understand anything that I'm saying. Don't fear that it's not going to be at a high enough level. So before there was quantum mechanics, there was classical mechanics, right? Isaac Newton, this man over here, and he had a certain way of looking at the world, that the world was full of stuff, and the stuff had a location in space, and it had a momentum. And it was this guy, Pierre-Simon Laplace, that figured out that if you were just given that information about everything in the world, the position and the velocity or the momentum of every piece of stuff in the world, and you had infinite calculational power, he said, what if you had a vast intelligence? And it was later commentators who said they labeled it Laplace's demon. He never called it a demon. I don't think he was religious. These days he would call it a computer. But the point is that if this computer, vast intelligence, had enough information about the universe today, to it, the past and future would be completely known just from information about the present moment. That's really the heart of classical mechanics. It gives us a clockwork universe. And then, of course, people believed this, bless their hearts, for hundreds of years. They thought this was basically the right paradigm for doing physics. The only thing left to figure out was what is the specific stuff and how does it move, what are the forces, and so forth. And then quantum mechanics came along and messed everything up, okay? So if you learn the rules of quantum mechanics in your textbook, in your classroom, they will look something like this, and they start off not that different from classical mechanics. Classical mechanics says there is a state, which in this case is positions and velocities or momenta, and there's an equation, Newton's law, that tells you how things move. Quantum mechanics says there's a state, which is in this case a wave function, and there's an equation, Schrodinger's equation, here's Schrodinger, that tells you how the wave function evolves. The problem is that quantum mechanics doesn't stop there. There's a whole bunch of extra rules, and all the extra rules that we teach our students have to do with what happens when you look at a system, when you measure it, when you observe it. You can only observe certain quantities, certain values. You cannot even predict exactly what the measurement outcome is going to be. The probability is the wave function squared. That's the Born rule. And after you observe it, the system changes dramatically so that it has a definite value of that observable quantity, even if it didn't before. So if you can put yourself in the mindset of physicists in the 1920s, from the data, they were confronted with this idea that, electrons had to be waves, otherwise they would just spiral into the center of nuclei and so forth. So there's an equation for dealing with that, the Schrodinger equation. But when you look at the electron, it leaves a path in a bubble chamber, so it looks like a particle. So it looks naively like physical systems act differently depending on whether you are looking at them or not looking at them. That sounds bizarre and wrong, so they came up with the following solution. Physical systems act differently depending on whether you're looking at them or not looking at them. And that does not really make anyone very happy. This is terrible. We teach it to our students, we have for the last 90 years, but it has this word observe or measure deeply embedded in the fundamental structure of our best physical picture of reality, without actually defining what we mean. When we say an observation, we don't say how quickly it happens, when it happens. We don't say, like, does a cat have the ability to make an observation? Does it have to be a human being? What if I just glance at it? What if my eyesight is not very good? Does that count as an observation? Why is it okay to treat observers as classical, even though systems are quantum and atoms are quantum and observers are made of atoms? Where does the probability come from? All of these questions are not answered by our usual way of teaching people quantum mechanics. So I like to say that, the 20th century, when it's remembered 500 years from now by historians of science, these historians are going to say, these people were just absolutely brilliant to invent quantum mechanics, and they completely dropped the ball in not trying to understand it very much. So just to drive this home, this is the one time I will appeal to authority in the talk. There's Richard Feynman, who said, I think I can safely say that nobody understands quantum mechanics. I did write an article for the New York Times recently where I quoted this, and I was very impressed. Only one physicist emailed me to say, I understand quantum mechanics. I don't see what's wrong with all these other people. Of course, Feynman he wasn't really saying that literally nobody understands quantum mechanics, but what he meant was, no one thinks that anyone else understands quantum mechanics. We do not have a consensus within the field about what quantum mechanics is actually about. Even though we set up these rules with Bohr and Heisenberg and so forth, even at the time, people like Einstein and Schrodinger were saying this is not good enough, we need to do better. But as a field, we decided to not try to do better. And I think that is not okay. That is the weird thing, that we haven't really tried to understand quantum mechanics. So it's worse than that. It's not that we tried and failed, that you would think that given the central role of quantum mechanics in all of modern physics, and the fact that we don't truly understand it, trying to understand quantum mechanics should be the high status subfield within our discipline, right? People trying to understand quantum mechanics should be the intellectual superstars of physics. Harvard and Princeton should be throwing money at them, trying to attract them from each other and so forth. But instead, if you try to understand quantum mechanics, you are kicked out. You get fired. I think that's the problem. So I like to illustrate it with the famous fable from Aesop, Aesop's fables. This is the fox and the grapes, and the fox sees the juicy grapes up there, says, I want those grapes. But the fox jumps up to get the grapes, and they're just too far out of way. They're out of reach of the fox. So eventually the fox says, you know what? I never wanted those grapes anyway. They're probably sour. So you're not supposed to explain your parables, but just to make it clear, the fox represents physicists. The grapes represent understanding quantum mechanics, and I think that we should be able to do better. So I'm going to skip a lot of history. I'm not going to go into any detail about the foundations of quantum mechanics. I just want to tell you the correct answer to these problems, which is something called the many worlds interpretation, invented by Hugh Everett, who was a graduate student who then left the field after he got his PhD. And basically, you can think of Everett's work as more therapeutic than physics. Basically, he's saying, chill out. You don't need to work so hard to avoid some wacky consequences of quantum mechanics. So what he says is, there isn't any classical realm. Forget about human beings or observers being classical. Human beings and observers are quantum just like everything else. Wave functions do not collapse. What do wave functions do? They obey the Schrodinger equation. When do they obey the Schrodinger equation? Always, all the time. That's all they ever do. You think that wave functions collapse because you need to think a little bit more carefully about what you are. And if you think about entanglement, it makes it clear what is going on. The price you pay for this beauty and precision and rigor is that you have to believe there are multiple copies of the universe that are created every time a quantum mechanical measurement occurs. So in other words, for those of you who are fans of elegance and simplicity and worry that the many worlds interpretation violates principles of elegance and simplicity, let me remember to you the rules of quantum mechanics as we teach them to our students. I've already told you what they are. There's a space of states, Hilbert space. There's an equation, the Schrodinger equation. There's all these weird, bizarre rules dealing with observation. That's the textbook version. Here's the Veredian version. There's Hilbert space, and there's a function, there's an equation, the Schrodinger equation, which tells you how states move. That's it. That's the entire theory. It is manifestly obvious that this theory is way simpler and ontologically lean and mean than the ordinary textbook rule of quantum mechanics as we teach it. The trick is you have to show that this much leaner, meaner, simpler theory actually reproduces what we see. That's where the work comes in. So I'm going to spend 2 slides telling you how this reproduces the world we see. The trick is that quantum states become entangled with each other. There's not a separate wave function for the electron and the apparatus and the person. There's one wave function for the whole universe at once, and the subsystems have states that can be entangled with each other within that larger wave function. So let's simplify our lives by factorizing. This is a product of a system, like an electron that you're going to measure, an apparatus that is going to do the measuring, and literally everything else in the universe, which we group together as the environment. So for example, the environment includes all of the photons, all of the molecules of air in the room that are bouncing in to your apparatus all the time. So the environment includes a whole bunch of degrees of freedom that you don't control. So you start with the wave function of the universe representing a system that is in a superposition, let's say spin up and spin down. The apparatus says, I have not yet observed the spin. And the environment says, I'm just the environment, I'm doing whatever I want to do. But then you measure. And measurement, this is actually pre-measurement in some sense, means that the apparatus interacts with the system. And this interaction isn't magical or mystical. It doesn't care whether you're conscious or you're a video camera. There's the Schrodinger equation. And that tells you what happens when the apparatus interacts with the system. And what happens, if it's a good measuring apparatus, is that it becomes entangled with the system. So the plus part of the system becomes entangled with the plus readout on the apparatus, likewise for the minus. And the environment hasn't had time to respond yet, but then very, very quickly, the environment will interact differently with the apparatus depending on whether its pointer is going plus or minus. So the environment becomes entangled with everything else. That's what we call decoherence. And the reason why that's important is because it explains why the Everett interpretation can be thought of as a theory of multiple worlds. So you see here the famous Schrodinger cat experiment. Schrodinger's daughter once said, I think my father just didn't like cats. He put his cat in a box, he put poison gas in there, and there's a quantum event that could happen to break the bottle and release the poison gas. For my thought experiment, I'm going to replace the poison gas with sleeping gas so we can put the cat to sleep rather than killing it. There's no reason to kill the cat. But the point is that this happens, this is the state of the system after the system has evolved for a little bit so that the apparatus, in this case this hammer falling and breaking the glass, is in a superposition. But very quickly that entangles with the environment. The photons and the atoms in the box become entangled depending on whether or not the hammer has fallen and the cat is awake or asleep. So there's an evolution that is, again, not magical. It's just following the Schrodinger equation into what are called pointer states. One state is the cat is awake. The other state is the cat is asleep. Pointer states are those which are robust with respect to being monitored by the environment. So if a photon goes near the cat, it may or may not hit the cat depending on whether it's awake and walking around or asleep and lying on the floor. But if it's in one of those states, all the photons interact with it the same way. So the robust states are those that are macroscopically coherent. That's why the world looks approximately classical to us. Because if it didn't, if you saw something in the world that was in a macroscopic superposition, the environment would have immediately become entangled with it. And when the environment becomes entangled with it, these environment states become orthogonal to each other very, very quickly. And what that means, if you look back up here, is that whatever happens in this part of the wave function goes its own way, completely unaffected by whatever happens in this part of the wave function, because they're orthogonal to each other. That's why Everett's answer to the question of what happens when I open the box and look at the cat is, there become two of you, because there's a copy of you that exists on the branch with one copy of the environment, and the other environment is a little bit different, but different enough to be orthogonal in Hilbert space. It's as if they have become distinct, non-interacting worlds. So I could go into much more detail and be much more persuasive about this, but the real point I want to make is, at no point did I put in a bunch of worlds. I didn't invent some kind of multiverse just to make sense of quantum mechanics. If you believe that wave functions represent reality, and you believe that an electron, for example, can be in a superposition of spin up and spin down, then you should believe that in principle, you can be in a superposition of having seen the electron spin up and having seen the electron spin down. And you should believe that the universe can be in a superposition of many different measurement outcomes. And everyone agrees that the Schrodinger equation predicts that these superpositions really come to be in the course of ordinary evolution. So the branching into different parts of the wave function is there whether you like it or not. As Ted Bunn once put it, every other interpretation of quantum mechanics is a disappearing worlds interpretation. The worlds are always there. The question is, can you live with that, or do you react against that so viscerally that you have to change the equations to somehow get rid of them? And that's what people do. But there are questions about this picture. One question is, why do we say that the answer to a quantum measurement is probabilistic rather than definite? In the Copenhagen interpretation, you just say it, right? You just make it up. It's one of the axioms. But Everett has no room for indeterminism. The Schrodinger equation is completely deterministic and completely reversible. You know that this pictorial version of the cat, the apparatus, and the observer will evolve into this superposition. In what sense is there anything probabilistic about anything at all? And the answer is, at this stage, and you notice that I've done this stage very quickly so that the apparatus has become entangled with the cat and the environment, but the observer has not yet become entangled. So decoherence happens very, very quickly. Tiny, tiny, tiny fraction of a second, 10 to the minus 20 seconds for a large macroscopic system. That's so quick that you do not have time to notice, okay? There will inevitably be a short period of time when there are two copies of you, or more than two copies of you, one each on the different branches of the wave function, but those copies are identical. So at this point in time, you have two people, not just one, and those two people can ask themselves, what is the probability that I'm on the branch where the cat's awake or the branch the cat's asleep? And then there's math involved, and you have to figure it out, but there is a unique answer, which is the probability is the wave function squared. It's exactly the Born rule. So the interpretation of what probability is different in many worlds, but the answer is exactly the same. It's that you should act as if the world is truly stochastic with probabilities given by the wave function squared. Sadly, not everyone is convinced by this, so they continue to work on alternatives. That's not actually sad. I'm happy that people are working on alternatives. I'm only sad when people don't care about the foundations of quantum mechanics at all. But the foundations are pretty out there. The alternatives, I should say, are pretty out there. One is that there are hidden variables. So Bohmian mechanics, for example, is an idea that there's a wave function, obeys the Schrodinger equation, but it's not all that there is. There are explicit particle variables, positions of particles, over and above the wave function. And in fact, the wave function evolves exactly according to the Schrodinger equation, but the particles are pushed around by the wave function and don't push back. The particles do not have any effect on how the wave function evolves. But the nice thing, that's the bad part, and the guidance equation for the particles is highly non-local in space. That's also bad. The nice part is that when you observe a quantum system, you're actually measuring the particles. So it actually answers this question, why is it that quantum systems look like waves when you're not looking and look like particles when you do look? Because there actually are particles there that you're finally seeing. There's another alternative called the GRW theory, Girardi, Rimini, and Weber. There's a version of this from Roger Penrose. In both of these theories, the wave function just collapses all by itself. There's a probability per unit time that the wave function will violate the Schrodinger equation and spontaneously collapse. It could happen. The nice thing about these theories is that they are experimentally testable, and people are trying to test them, so that's a good thing. But I'm not going to talk about those anymore. I just want to let you know they exist. And in comparison, the many worlds approach is a little bit more pure in terms of how quantum mechanical it really is, right? If you think about these alternatives I just showed you, in some sense, they're not quite letting go of the classical precursors. There's particles that have locations, or the wave function collapses to a location in space just like a classical particle would have. Whereas in many worlds, the wave function is just a vector in a giant dimensional, complex, normed vector space called Hilbert space. All the vector ever does is obey the Schrodinger equation. It branches into distinct worlds. So what's missing from this, the difficulty in many worlds, is that the underlying formalism is very lean and mean and pure and austere and pretty, but it looks nothing like our world. There's no tables or chairs or space or fields or anything like that. Thus, the real challenge for many worlds folks is recovering the richness of the world of our experience, starting with just a vector in Hilbert space. So, in other words, in yet other words, all of the classical notions that we're so familiar with need to be derived if you're a many worlds person. Even if you're a very advanced theoretical physicist, we still find new theories that potentially describe nature by a process that includes usually starting with a classical theory and then quantizing it, right? You can learn a set of rules for taking a classical theory and turning it into a quantum mechanical theory. But presumably, nature doesn't do that. Nature just is quantum mechanical from the start. And what you should try to do is start with a vector in Hilbert space and explain why you can interpret this vector in Hilbert space as tables and chairs and planets and people moving through three-dimensional space, etc. So rather than presuming some positions in space and talking about that from the start, just think about an abstract vector and derive how everything else emerges from that naturally. We call this program Mad Dog Everettianism. It is the most extreme form of Everettianism because even a typical Everettian will assume some classical structure of preferred observables or something like that. In this point of view, we just give you the bare bones ingredients that define a quantum theory, which are Hilbert space, a Hamiltonian, and a state. Everything else gets derived. So that's not a lot of data. You have the dimensionality of Hilbert space. You have the energy eigenvalues of the Hamiltonian, right? When I say I give you a Hamiltonian, I can't give it like in terms of derivatives or momenta or things, because those already presume that I'm acting on certain subsystems in certain ways. The only independent way to give you the information that defines a Hamiltonian is in the energy eigenbasis, and I give you the energy eigenvalues, which is the spectrum. And then I give you the complex numbers that define the state. Still, it's not that many numbers. And from this, you want to derive all of reality. That's the challenge. Sadly, I'm not yet out of time, so I can't just leave it as homework. I can't finish this project in the next 40 minutes. Sorry about that. But I want to tell you about two directions that we're pursuing in making progress in this. So the big challenges go from a wave function in Hilbert space to reality, especially to the semi-classical reality in which we live. So the two things I want to talk about are what this says in terms of cosmology. I grew up as a cosmologist. I still enjoy cosmology. So what does this teach us about the origin of the universe, the nature of the late universe, and so forth? And also gravity, like the single biggest challenge that respectable physicists would admit still exists in physics, is reconciling gravity, Einstein's general relativity, with quantum mechanics. And I think that a big reason why we've been held back, why this is so difficult for us, is that we insist on starting with a classical theory and quantizing it. Not necessarily general relativity. String theory is a classical theory that we then quantize. That's the first thing you learn in your string theory course, is how to quantize a vibrating string, right? I suspect that the best way to get a theory of gravity isn't by starting from a classical theory and quantizing it. It's to start from a quantum theory and ask what are the properties it might need to have to successfully emerge space and time as we know it. So here's this little chart, a little finder chart that I made for you astronomers in the audience, way back when I was an astronomer. So if you want to define what you mean by quantum cosmology in Hilbert space, that means you're studying the wave function of the universe as a whole. It's an interesting historical fact that Hugh Everett, when he invented the many worlds interpretation, his advisor was John Wheeler, who gave him the project not of finding a new alternative to the Copenhagen interpretation, but of quantizing gravity, of thinking of the wave function of the universe. And the first thought that Everett had, there was apparently a long night with a lot of sherry being consumed. But what came out of it was, if you're quantizing the whole universe, you can't stand outside it and be an observer, right? So the traditional rules of the Copenhagen interpretation didn't work, and he ended up inventing many worlds. But there's two questions you should ask yourself right away. Is Hilbert space finite dimensional or infinite dimensional? That's one thing you could ask. The other is the Schrodinger equation the fundamental equation, or is this weird equation the fundamental equation? So the Schrodinger equation says h psi equals I d by dt psi. The rate at which the wave function is evolving depends on the Hamiltonian. But there's a special case of this equation. So it's not a whole new equation, but there's a special case which just says you're in the zero energy eigenstate. There's no time evolution at all. H psi just equals 0, not I d by dt psi, okay? So all four of these boxes are a priori quite amenable to analysis. You can think about what the universe would be like in this case, okay? So if h psi equals 0, the parameter t representing time does not appear in the equation. So you might think this is ruled out by observation, since time seems to pass, okay? Physicists, as you know, are more clever than that. So what this really means is that time is emergent. Time is not fundamental. And I'm not going to pursue this a lot in the rest of the talk, but one of the big challenges for quantum cosmology is showing why time exists at all. This equation, h psi equals 0, does naturally fall out of quantizing general relativity. I'm not in favor of quantizing general relativity, but it still might be the right way to go. And if you do that, you need to emerge time out of the wave function, just like you need to emerge space and particles and everything else. If time is emergent and the dimensionality of Hilbert space is finite, then there's only a finite number of moments of time that there are to be emerged, right? There's only a finite number of states in Hilbert space that are distinct from each other. So in this case, the universe has a beginning, it also has an end. If h psi equals 0 and dimensionality of Hilbert space is finite, the whole extent of the history of the cosmos is finite in duration. You might think that fits well with the Big Bang model, and that might be true, but it also predicts doom at some point in the future. If the dimensionality of h equals infinity, this is the hardest question. So if time is emergent and space and Hilbert space is infinite dimensional, then we don't know whether the universe had a beginning or not. Time is emergent, so it could work either way. Presumably, time goes on infinitely, but I don't know if it goes from minus infinity to infinity or 0 to infinity. Either way works equally well. The case that I'm sort of more interested in is when we don't live in an energy eigenstate, when it's really the Schrodinger equation, then time is fundamental. Then, if the dimensionality of Hilbert space is finite, you have an infinitely long time and only a finite number of states in Hilbert space. So guess what? The same thing happens over and over again. You end up in some Nietzschean nightmare of eternal recurrences where this lecture hall with us in it appears an infinite number of times in the history of the universe. And the bad news is that most of the time when this room appears, there's nothing outside, right? The rest of the universe in thermal equilibrium plus this room will appear way more often than this room embedded in a nice, comfy city in Vancouver in Canada with the solar system and all that stuff. So this is terrible, this box. This is the one box I can say, we don't live in that box. That'd be a bad box to live in. So if you really have the Schrodinger equation, then probably the dimensionality of Hilbert space is infinite, which has interesting consequences. So what do we know about these? I mean, is Hilbert space infinite dimensional or finite? Well, if you might think, finite is easier than infinite, but then you start doing quantum mechanics, this is a terrible, I think I'm blaming your projector for not projecting this very well. The simple harmonic oscillator is something you will learn in your quantum mechanics course. Even a single simple harmonic oscillator has an infinite dimensional Hilbert space because there's a zero energy state, first excited state, second excited state, all the way up. So very quickly when you learn quantum mechanics, you get used to the idea of Hilbert space being infinite dimensional. In the real world, there's a reason to think that's not right. And that reason is called gravity. Okay? I take a box and I put energy in it, trying to get more and more quantum states inside the box, but eventually the box collapses into a black hole. And if I ask how many states can I fit in a box of finite size, I cannot put more energy in there than would equal a black hole that just barely fits into the box. So this was pointed out by Jacob Bekenstein, and he argued that in quantum gravity, there's only a finite number of states that you can fit into any region of space-time. So that's a finite dimensional Hilbert space representing anything that can happen in one region of space. I think this is basically right. Like, this is hard because we've abandoned the project, or at least neglected the project of understanding quantum mechanics at the fundamental level for the past 90 years, and we haven't really focused on this sort of quantum first Hilbert space version of reality. People's opinions differ about whether or not Hilbert space is finite or infinite dimensional, but this is, I think, the right way to go. We even have an idea of what that dimensionality is. It's not just that it's finite, it's that we know what it is. We know what the entropy of a black hole is, right? Stephen Hawking and Bekenstein in the 1970s worked out a formula for the entropy of a black hole. It's proportional to the area of the event horizon in Planck units. So roughly speaking, it's the size of the black hole in linear size in Planck units squared. Why does the entropy matter in any way? Because the entropy, I realize just now I will only explain this later in the talk, but the entropy tells us how many states there would be if you're at the maximum entropy state. So in other words, if you have a Hilbert space of a certain finite dimensionality, and you say, what can I do to that little subsystem of the universe to put it in a maximum entropy state, the entropy of that state will be the logarithm of the dimensionality of Hilbert space. That's a formula you can derive. There's a lot of squiggles here. I'm not getting the 4 pi's correct, but this is morally correct. So the dimensionality of Hilbert space, if you're in a maximum entropy state, which a black hole is e to the entropy. So the dimensionality of a region of space, of the factor of Hilbert space representing what can happen in one region of space, is something we think we know. It's e to the area of the boundary of that region in Planck units squared. This is a big number, as I'll say in a second, but it's still a finite number. And the fact that Hilbert space is finite dimensional might have incredibly important consequences for how nature works. There's a technical point about locality that if you're a quantum gravity expert, we can talk about later. Okay, it's not just black holes. Black holes have a horizon that has an entropy, but we live in an accelerating universe. Some of you might have been told that in 1998, is there anyone who wasn't yet born in 1998 in the room? Oh, man. When I was your age, the universe was not accelerating. But now, we've discovered in 1998 that the universe is, that if you look at a galaxy very far away, not only is it moving away from us, but they're moving away from us faster and faster, the acceleration of the universe. We attribute this to the idea that empty space has energy, the vacuum energy or the cosmological constant, which tends to push things apart. In the 1980s, Bob Wald proved a theorem called the cosmic no-hair theorem, which says that if you live in a universe with vacuum energy pushing things apart, then that wins over everything if you wait long enough. This makes perfect intuitive sense, right? Not only are galaxies, et cetera, moving away from us, but they're moving away from us faster and faster, and they're being replaced by nothing but empty space. So if you just wait long enough, eventually the stars will die out, all the dead stars will fall into black holes, all those black holes will evaporate, and a Google years from now, 10 to the 100 years from now, that was what the word Google meant before Silicon Valley came along, we'll have nothing but empty space. And the world will be smooth and featureless, and that is the highest entropy state. That is the cosmological equivalent of a black hole. And around us, there will be a horizon, and that horizon has an area, and that area gives us an entropy for the region we live in. So in fact, Aidan Chatwin-Davis and I proved a version of this theorem, of the cosmic no-hair theorem, using the second law of thermodynamics. We used a particular way of defining entropy in an expanding universe to show that simply saying entropy increases, but not forever, it asymptotes to a maximum value, that assumption implies that the universe empties out and approaches this cosmic no-hair state, which we call de Sitter space. So you can think of the tendency of the universe to empty out and accelerate as a reflection of the second law of thermodynamics, of the fact that entropy increases. So you run the numbers, you know what the vacuum energy gives us for a size of the horizon around us, and you find that the entropy of our patch is roughly 10 to the 120. So the dimensionality of the part of Hilbert space representing our universe is roughly e to the 10 to the 120, which is a very big number. Trust me on that, okay? But it's still finite, it's still less than infinity. So this is the picture that we have. We live in the middle of this region labeled O, and it's finite in size, has a finite area boundary, and then something is going on outside. Okay, this is our observable universe, and this is the exterior. And what we think is true is that the Hilbert space of the universe is our observable universe producted with the external universe. We think we know the dimensionality of this thing. It's pretty big, but not infinite. We have no idea whether the dimensionality of the outside region is finite or infinite, except that I gave you an argument that it better be infinite, right? Because if it's not infinite, then we should recur and cycle back, and that would be bad for all various reasons. So the motto then is that Hilbert space is locally finite dimensional. Within the region of space that we can have access to, that we can observe, there's only a finite number of quantum states that could possibly live there. Maybe an infinite number in the rest of the universe, but locally just a finite number. And what that means is, for those of you, have you had quantum mechanics already? You were born after 1998 and you've already learned quantum mechanics. This is getting more and more depressing as I'm getting older. All right, so then you know what this means. You could explain this? No, that's okay. I'm not going to make you explain it. Don't worry. Don't be upset. I'm not going to take my angst out on you just because you're young. There's a math fact that if Hilbert space is infinite dimensional, then there's many, many different ways to define an infinite dimensional subset of Hilbert space that corresponds to a given physical theory. There are different ways of defining algebras of observables, things you could potentially observe within that Hilbert space. They're all different as long as Hilbert space is infinite dimensional. But if Hilbert space is finite dimensional, which I'm saying our little observable universe corresponds to, then you can observe whatever you want in a very well-defined set of operators called Hermitian operators. So in other words, what that's saying is, if Hilbert space is locally finite dimensional, we can't rely on some preferred notion of what can be observed. We should be able to derive what can be observed and why it's natural to express cats in the awake or asleep basis rather than 1 over square root of 2 awake plus asleep, and 1 over square root of 2 awake minus asleep. Why is that the bad basis to use? All right. So I told you that you're going to stop understanding as we go on. Here we go. We're going to stop understanding now. If you believe that we, have a universe that at the classical observable level has all the features we know and love, space is expanding, there are galaxies and so forth, but now I'm telling you that there's only a finite dimensional Hilbert space describing all of that. There's a lot of work to be done in showing how that is even possible. How in the world can a finite dimensional Hilbert space describe all the world around us? So for one thing, what happens when space expands, right? So there's always this mystery when space expands, because we often in quantum field theory talk about degrees of freedom as modes of vibrating quantum fields. And the best way to describe those modes in an expanding space is, someone's beeping, yeah, they're running away. So the modes themselves get stretched with the expansion of the universe. So if you believe that there was some minimum distance, the Planck scale or something like that, at which physics made sense, but space is expanding and it's getting bigger and bigger and the modes are stretching along with it, there were modes that were smaller than the Planck scale that are now bigger. So where did they come from? So here's a suggestion for what might be going on. Maybe space-time itself is knitted together by a finite number of degrees of freedom that are entangled with each other. And the more degrees of freedom that are entangled, the bigger space is. So maybe what it really means to say that the space is expanding is that there's a whole, I don't know why I say it yet, there's a whole bunch of quantum degrees of freedom that are initially unentangled with each other. These are called ancilla degrees of freedom. And if you're thinking about going up to study quantum computing, you will learn about quantum circuits. So a quantum circuit is kind of like a classical circuit diagram where you get a bunch of bits coming in, a finite number, and a finite number of bits coming out. If you think that Hilbert space is finite dimensional, quantum circuits are a very natural way to represent the evolution of a system. And so what this is saying is maybe the expansion of space is really a bunch of unentangled qubits becoming entangled one by one with the rest of space, and space is just getting bigger because more and more qubits are becoming part of that entangled ensemble. This is an interesting, slightly askew version of how we should think about the expansion of space with an intriguing consequence. Many people like to imagine inflation as a process that happened in the early universe, and we often say inflation happened for a certain number of e-folds. That is, the universe expanded by a factor of e over and over again n times, capital N times. And you will hear people say, in classical inflationary cosmology, there's a minimum number of e-folds we need, which is 60, but there's no maximum. You could have as many e-folds as you want, it doesn't really matter. But here, there's kind of a maximum in this picture, because you can only entangle a finite number of qubits because we know what the total size is that you can fit into our observable universe. And you're entangling them as space expands, so you can wind the clock backwards and say, well, when did it all start with only one qubit? Or actually 2 qubits entangled with each other. And the answer is, at most, 75 e-folds before the end of inflation. So from this quantum circuit cosmology perspective, inflation doesn't go on forever. In fact, it doesn't even go on that much more than what we can observe. So talking about what the universe was doing before 75 e-folds before the end of inflation is meaningless, physically meaningless in this picture. I would like to be able to derive some observational consequences of this perspective, but we haven't been able to do that yet. Maybe some young people in the audience will do that. Here's another question that we can address. I've alluded to this, the Boltzmann brane problem, okay? The Boltzmann brane problem is the idea that rather than you and I coming into existence as the result of ordinary thermodynamically sensible evolution from the hot Big Bang to today, what if the universe was just kind of like a box of gas, a bunch of particles randomly bumping into each other that lasted forever? If you have randomly bumping into each other particles lasting forever, eventually they will make all sorts of interesting configurations. And if the box is big enough, that could include you and me. You and I could come into existence not by evolution and having parents and stuff like that, just by being random assembled just by luck. It seems very unlikely, but if you take a small probability of something happen per second and multiply it by infinity seconds, it's going to happen. So naively, the picture that we have of the accelerating universe is exactly like a box of gas that lasts forever with a certain temperature. De Sitter space, this accelerating universe, has a temperature roughly equal to the Hubble constant. It's kind of like you and I live in a box of gas. Not very hot, this is a very cold temperature, but eventually it's there. So it's kind of like a bunch of things randomly fluctuating into existence, and this causes the problem that if you wait long enough, even though you and I will fluctuate into existence much more often, so I should back up to say, in this infinitely lasting box of gas, fluctuations into lower entropy states happen, but small fluctuations happen way more than big ones. So really the prediction that this scenario makes is that an intelligent observer in this cosmology should be the minimum fluctuation downward in entropy that is required to make an intelligent observer. The idea is that that minimum fluctuation would be just enough atoms coming into existence to form a brain that then looks around and goes, ha, thermal equilibrium, and then it dies. This is called a Boltzmann brain, and then you go, well, I'm not a Boltzmann brain, so this theory is ruled out. There's logical loopholes there that I'm not going to point out, but that's basically the idea. So with Jason Pollock and Kim Boddy, I pointed out this is also nonsense. This argument is not right, or at least it's probably not right depending on the dimensionality of Hilbert space, okay? In a quantum state, it's interesting. Well, I didn't do that. I didn't go into all the details of what is meant by temperature in the quantum mechanical sense. If you have a classical box of gas at a certain temperature, that means there are some molecules in the box. You just don't know the position and velocity of every single atom or molecule. You have some probability distribution over them. In a quantum thermal state, there's nothing that is actually moving. There's nothing that's actually fluctuating. If you just let the universe expand until everything dies out and cosmic no-hair kicks in, you approach a unique stationary quantum state. It is true that if you added to that state a thermometer, that thermometer would in fact measure random particles bumping into it and with a thermal spectrum, but there isn't any thermometer there. And we're not being Copenhagen. We're not observing the universe from outside. From within that universe, you just approach a steady state and stay there forever. There are no real quantum fluctuations. Therefore, here's the conclusion. If the dimensionality of the total Hilbert space of the universe is finite, then there is indeed a Boltzmann brain problem. Forget about, the Big Bang and so forth. The universe will last forever. There'll be tiny fluctuations. Most observers will be Boltzmann brains. But if we live in a finite dimensional part of an infinite dimensional Hilbert space, our little part dissipates out into the bigger environment around it. It settles down into a stationary state, and nothing ever fluctuates. Does anyone know what this picture is? I have this picture up here that makes no sense in this context, right? This is the wave function of an electron in a helium atom. They measured it. This is data. This is not just a picture. I said you can't measure wave functions, but they very gently touch it over and over again and just disturb it a little bit. And so this is an actual stationary quantum state. There's nothing moving in it. Again, we tend to think in classical terms even though we know better. We tend to think of the electron as a little dot which is moving around inside the wave. But it's not. This is the electron. The electron is the wave. And that wave in the stationary quantum state of the future empty universe is perfectly stationary, not making Boltzmann brains. Okay. The last topic I wanted to mention in this context is the emergence of space-time itself. So there's been a lot of excitement in the last several years about how space-time and the geometry of space-time can emerge from entanglement between quantum degrees of freedom. Mark van Ramsdonk here at UBC has been a major force in this effort, but almost all of this effort has been in the context of what's called the Ats Cfd Correspondence. So this is a favorite thing to examine for string theorists and their string theory adjacent friends, where there's this wonderful fact invented by Juan Malacena, discovered by Juan Malacena back in the 1990s, where you can define a field theory in flat space and show that it is secretly the same as a theory of gravity in one higher dimension. That's the good news. The bad news is that theory of gravity in one higher dimension has a vacuum energy, a cosmological constant, that is negative. Our universe has a vacuum energy, a cosmological constant, apparently, that is positive. So here is where you have to declare your tribal affiliation. You can say, I like negative cosmological constants better because they give me the Ats Cfd correspondence and I can calculate a whole bunch of interesting things and write papers about them. Or you can say, I like the positive cosmological constant because I live in the world. And I'm actually a big believer, I'm all in favor of doing the Ats Cfd correspondence and calculating things within it, but I would just want to keep our eyes on the prize that eventually what we want to do is understand why apples fall from trees and why the Earth orbits the sun and things like that, gravitational phenomena that are purely local and do not depend on asymptotic boundary conditions. So, in the Ats Cfd case, the entanglement that you're talking about that gives rise to the emergence of space-time is entanglement of quantum degrees of freedom on the boundary of the universe infinitely far away in ADS space, in this hypothetical mathematical model with a negative cosmological constant. What we want to ask is there a version that is much more simple, down to earth, of entanglement here in this room, giving rise to laser pointers falling toward the Earth? In other words, can we work directly in the bulk? Well, we can take a hint. We know what physics should look like at low energies, weak curvatures. It's quantum field theory. Quantum field theory works very well in everyday circumstances. And there is a feature of quantum field theory which is worth emphasizing if you haven't done quantum field theory yet. Namely, that in quantum field theory, empty space is a really exciting place. Like if the world were made of particles, you might think that there are particles at locations or they have wave functions, but in between the particles, space is empty. There's nothing happening, right? There is nothing but atoms and the void, as Democritus put it. Or maybe Epicurus, I think. I think it was Democritus. In quantum field theory, that's not what the world is like. So fields are in some sense the opposite of particles. Particles have a location in space. They are here and they are not anywhere else. Fields have a value at every point in space. That's what a field is. At every point, the field has a value. The value could be zero, but you think about the electromagnetic fields, the gravitational field, etc. In quantum field theory, even matter particles like neutrinos and quarks and electrons are vibrations in a field that fills all of space. So in quantum field theory, a particle is just a field that is vibrating more than usual. Empty space is not completely empty. Empty space is just where the quantum fields are vibrating as little as possible. They are in their vacuum states. They are in their lowest energy configurations. So you can ask questions about how the different quantum field theory modes are entangled with each other in empty space. So you can ask the following thing. Can you take all of these modes of a quantum field and, let's say divide space into little boxes and can think of the Hilbert space of space, if that's okay, as the product of what's going on in all these little boxes. And then you can say, well, what if I want to link together all of these different things going on in space in such a way so that physics looks local, right? Physics looking local means if I poke the field at one location, it doesn't instantly affect things very far away. The effects ripple out at the speed of light or more slowly. This is built into the structure of quantum field theory. What does this tell us about the fundamental laws of physics? Well, the fundamental laws from an Everettian, many worlds point of view, the fundamental laws, as we've said, are just the Hamiltonian. That's it. There's a Hamiltonian. Let's imagine everything is finite dimensional. Then at every point in space, there's some degrees of freedom, and the Hamiltonian will be the self-Hamiltonian of that degree of freedom, plus how it interacts one by one with all the other degrees of freedom, plus how groups of 3 degrees of freedom interact, plus etc. There's an infinite series here. And then there's a very special, that's a completely generic statement, there's a very special subclass of Hamiltonians which are K-local. That means K is a letter, and it means that there's a degree of freedom here. It will only interact with K other degrees of freedom. There's 0 interaction with all the others. So in other words, in principle, I can write any Hamiltonian as this infinite series, but if the series ends at some value K, so there are no higher order, higher point interactions, then I call it a K-local Hamiltonian. This is lingo borrowed from computer scientists who are thinking about circuits. So there's a wonderful paper a couple of years ago that says that if you just give me a typical Hamiltonian, which remember is just a list of the energy eigenvalues, there's no way of writing that Hamiltonian so that physics looks local. So if you just randomly pick some energy eigenvalues and say, can I write Hilbert space as the tensor product of a bunch of little factors interacting locally with each other? The answer is no. For some very specific Hamiltonians, you can, but it is not the generic case. For those when you can, locality is almost essentially unique. That is to say, just from knowing the energy eigenvalues, I can pick out the right way to decompose locations in space so that interactions look local. So the fact in this picture that space looks three-dimensional is baked in to the energy eigenvalues of the Hamiltonian of the universe. Had they been something else, space would have looked five-dimensional or something like that. So what this means is we can play the game that we said we wanted to play. You can be given the Hamiltonian of the universe and figure out, oh, this is how I should decompose the degrees of freedom in my quantum state so they look like a bunch of things interacting locally with each other. So we're left with this kind of thing, this kind of lattice network structure, graph structure, where different little parts of the Hilbert space of the universe interact with their nearest neighbors, but not with things further away. What that gives us, in other words, is a topology to Hilbert space. Hilbert space is some gigantic vector space, but here we're saying we can write that Hilbert space as the product of many little subvectors, and there's a right way to do that so the subvectors interact with each other locally. But can we do more? Can we take this lattice or this network and put a geometry on it, not just the topology? Well, again, we can use a clue that we get from quantum field theory. When we have in quantum field theory, there's an infinite number of degrees of freedom there, but putting that aside, we know from solving the equations that degrees of freedom that are near each other tend to be highly entangled, and degrees of freedom that are far away from each other are not very entangled at all. So we can ask what happens if we turn that around, if we reverse engineer this. So ordinary quantum field theory takes space and its geometry as given and derives that the quantum fields have this entanglement structure. We don't have space and geometry as given, but we have the entanglement structure, so let's just reverse it. Let's just say what we mean by being nearby is when 2 degrees of freedom are highly entangled with each other. What we mean by being far away is when they're not very entangled with each other. So this is a measure of entanglement, and this is the distance. And we're going to put an ansatz that says that's how geometry is defined. For those of you who have taken general relativity, if I know the distance along any curve in space, I know the entire geometry of it. So how do I know how entangled things are? This guy, John von Neumann, gave us an equation that basically lets us figure out how entangled one set of degrees of freedom is with the rest of the world. Remember, there's this thing called entropy, which in classical physics is roughly a measure of how much you don't know about the microstate of a system. When you're in a high entropy state, that's a way of saying it could be doing anything. When you're in a low entropy state, you have a pretty good idea of what it's doing. So von Neumann noticed that in quantum mechanics, there's a whole new way that entropy can come to be. If you have two subsystems, A and B, you can know everything there is to know about the combination of A and B, but they can be entangled with each other. So A could be a spin, and B could be a spin, and you could know that the spins are in the same direction, but you don't know what either one is. So there's no entropy overall, but for a subsystem, if you ask just about A, there's something you don't know, because it's entangled with B and you've forgotten about B. So there's automatically an entropy in A just because it's entangled with B. And you can use that to quantify how much entanglement there is. So here is another proposal, another ansatz. Again, this is very, very sketchy, early days kind of work in this field. If you have a very typical lattice of points, and they're interacting with each other just with their nearest neighbors, short-range interactions, in the lowest energy state for such a system, it will happen that the amount of entanglement between the interior of some surface and the exterior is proportional to the area of that surface, of that boundary, okay? That makes perfect sense, because deep inside the region, there'll be degrees of freedom that have almost no entanglement with the outside. All the entanglement comes from degrees of freedom that are right there on the boundary, so they're basically telling you how much boundary there is. It makes perfect sense that entropy is proportional to area. But that's only true in the vacuum state. I could make non-vacuum states where the degrees of freedom inside are highly entangled with anything that I want. There's no necessary relationship in a random quantum field theory on a lattice between entropy and area. So here's the ansatz, here's the guess. What if gravity makes it the case that in any region of space, the entropy inside is always proportional to the area around it? In other words, I can change the quantum state to increase or decrease the entanglement, but geometry will then change to compensate. The geometry of space itself, which defines the area of that surface, will be warped by that change of entanglement, so that it always remains true that the amount of entanglement is proportional to the area. This is an ansatz, but it's an interesting one. What it gets us is the following. We know that the geometry, well, we've asserted that the geometry of space goes like the entanglement. I think I missed a slide here. All right, there's another slide I had which is really awesome, which it explains that the amount of entanglement is also proportional to the energy inside. If you change the energy inside, I think it's the next slide, yeah. Oh no, I didn't use energy. I'm still good. Never mind, I'm still good. We can measure the entanglement using the entropy. I should have just put this one first. That's just a true fact. Von Neumann said that. That's not up for dispute. The ansatz that we have is that the geometry of space emerging from this amount of entanglement is proportional to the entanglement that we have. If only it were also the case that the entropy in a region somehow tracks the energy in that region, then we would have a relationship between energy and geometry, which is kind of what we want, kind of what Einstein gave us for general relativity. But guess what? Entropy and energy are naturally related. Even in classical thermodynamics, the flux of entropy is proportional to the heat divided by the temperature, and that continues to be true in a quantum mechanical context. It's a little bit harder to show, so I won't do it. There's something called the Entanglement First Law that you can go through relating the slight perturbation in the entropy of a quantum state to a slight perturbation of its energy. Roughly speaking, vibrating modes next to each other are naturally entangled. If you unentangle them, that takes energy to do that. So when you put it all together, you are left with the geometry of this emergent space that is defined by its entanglement changes when you change the energy inside. But that motto, geometry is proportional to energy, is just general relativity in words. I mean, there's more to it than that. There's some equations and things like that. Here's the equation that Einstein wrote down, but I'm skipping some steps. The actual thing that we are able to derive is, here's a list of assumptions for how the emergent geometry could respond to the entanglement, and out of that we derive, in the weak field limit, Einstein's equations for general relativity. So this is very similar to what they've done in the Ats Cfd correspondence in different contexts, but it's right here in the room. It's right here in the weak field. It's an encouraging sign that we can get gravity out of quantum mechanics. So rather than quantizing gravity, rather than starting with some classical theory of curved space-time and applying the rules of quantum mechanics to it, we can just start with the rules of quantum mechanics, point to different features of the quantum state, and go, there is gravity, there is space-time. It is very naturally warped as the entanglement changes, and that warping very naturally obeys Einstein's equation. That can't be the entire story. This can't be the final answer. This can't be completely right, because we know that the universe is not a little lattice of things that have nearest neighbor interactions. I'm not going to go through the details here, but what we know about black holes and how they evaporate indicates there is more to the story. However, what is more to the story is completely compatible with the idea of putting it together at the level of Hilbert space and wave functions, just wave functions that are not quite local in the conventional sense. So this is ongoing work that we're trying to do right now to try to fit black holes and holography and complementarity into this picture of emergent space-time. All right, just to conclude, last slide. Here's what we're trying to do. We're trying to start with nothing but a quantum wave function, a vector in a big Hilbert space. We're using entanglement between different parts of that wave function to define an emergent geometry. What we get very naturally in the classical limit, in the weak field limit, is Einstein's equation of general relativity, which is pretty good. There's a lot more to do. We're not done yet. It's full employment for theoretical physicists. But I think that what's important here is that this idea that we should try harder to understand quantum mechanics isn't just a moral imperative, although it is that. It's not just that it's our job as physicists to try to understand nature as well as we can. Even the questions that we all agree are important and sensible and pressing, for instance, how to reconcile gravity of general relativity in quantum mechanics, might rely on an improved understanding of the foundations of quantum theory. So I think it's finally time to prove Feynman wrong and make it the case that we all understand quantum mechanics. Thank you very much.